Hi, and welcome to this video on the section of the course that is all about forces. And what we're going to be doing is talking all about the big man, Sir Isaac Newton, and his three laws which underpin absolutely everything that we're going to be doing on the mechanics course. So essentially what we're going to do is, in a series of videos, take you through his three main laws and how we're going to use and apply those to understand how forces interact with motion. So here we go. So we've got Newton's first law. We've got this idea of resultant, when you get multiple forces acting on an object. We're going to introduce some vector stuff, and then we're going to have a look at Newton's second and third laws as well. But like I said, we'll get to all of that. So here we go. To begin with, Newton's first law and resultant forces, and a bit of vectors work. So off we go. Right, Newton's first law. Every object remains in a state of rest or of uniform motion in a straight line unless forces act on it to change that state. And that came from his the big old book that he wrote in 1686, Principia Mathematica Philosophiae Naturalis, and I always trip over the title of that one. And that was his big work that really established him as that kind of the big man when it came to mathematics and physics. And it is fairly obvious. It doesn't look entirely straightforward to begin with, but when you start thinking about it, it is fairly straightforward, as we'll see. So we've got an object if an object's going to accelerate, then some force must be acting on it. And the more force that is applied, the greater acceleration, which is all fairly obvious. And that motion is unchanged when the forces are in equilibrium. And this is the key to it. So what we're saying is an object is in a state of rest, i.e. it's not moving, or the more less obvious bit is this uniform motion bit. So if it's travelling at a constant speed, then the forces will be in equilibrium. The forces going in one direction will be exactly equal to the forces going in the opposite direction. And it's only when we get one force in one direction larger than the other that we actually get anything accelerating. So this idea of uniform motion, state of rest, basically the same thing in terms of, in both cases, the forces are in equilibrium. Now, force, hopefully you know from your physics, is measured in newtons, and 1 newton is defined as the force required to give an object of mass 1 kilogram and acceleration of 1 meter per second. And that might not seem particularly important, but as we see when we look at his second law, it's absolutely key and was like the big driver in everything that he managed to do. So, what does all that mean? Let's just have a quick look at a very, very simple example. Here we go. Here's a book dropping on his desk. And there you go. There's Newton's Principia Mathematica, what's it called, the thingy. And if it's falling, then the only force acting on it is gravity. And that's a force, so the book will accelerate. When it hits a desk, we've now got gravity acting still, but you've also got a second force. And that force is what we're calling the reaction force of the desk on the book. And at this point, those two forces are exactly the same. The force due to gravity is the same as the reaction force, so therefore the book is not moving. And that's what Newton was saying in his first law. It remains as rest as long as the forces are in equilibrium. These two forces have got to be the same, because this book is neither jumping off the desk and jumping up in the air, in which case, because if it was, then we'd have the reaction force bigger than gravity, and neither is it sinking through the desk, in which case, if it was doing that, then the gravitational force would be bigger than the reaction force. Clearly, common sense tells us that those two forces have got to be the same because the book is not moving. Now, if we do this horizontally, and if we apply a kind of force here to the book, what we've got is this push going that way, but initially the book's not going to move because there's a force going the other way, and in our example, that force is going to be friction. And again, those two things are going to be equal if we're only applying a small force. As we increase the amount of push, increase the force we're putting through this book going to the right, then the friction will get bigger in order to keep it equal so it doesn't move. But eventually what will happen is our push force will be bigger than the frictional force and the book will move, and that's the thing down here that said is the resultant. The difference between the force we're pushing the book with and the force going the other way, which was the friction. Right, when it comes to modelling questions throughout this mechanics course, we are modelling objects and we're modelling them as a particle, which means they're at a particular point, so they haven't got size and we haven't got to worry about air resistance, and all those forces are acting all at the same point, which just keeps the models a whole lot more simple. So what we've got is a diagram here. So we've got our particle, and we've got a whole load of forces acting on it. Some are acting in the vertical direction, some are acting in the horizontal direction, and we're told that it's travelling at constant velocity, and as soon as we see that constant velocity, that means we know that our forces are in equilibrium. So what we're going to do is have a look at the force, and we're going to spend a lot of time on this course resolving in different directions, so what that means is we're going to have a look at the forces that are acting in the horizontal direction, so that's those ones. So if it's in uniform motion, equilibrium, we know that these forces here are equal. So we can say that 2a plus b going in that direction is the same as the 9 newtons going in that direction. And then if we have a look at the horizontal forces, we've got 3o going up, we've got these two forces going down. So we've got that. And if we just tidy up this one on the right hand side, that tidies up to be a minus b equals minus 3. And hopefully now you can see where we're going with this one. In order to figure out the size of a and b, we're going to have to do a simultaneous equation. There we go, simple job of adding them together. And so we've calculated a and we've calculated b. Now, that one, because it ended up as a simultaneous equation, is slightly more complicated than your basic one. So if you want to just kind of pause for now and have a little practice at just kind of the real simple, the base ones, getting this idea of forces and equilibrium, then that might be a good idea. Or if you're feeling confident, we can just crack straight on. Exactly the same principle now, but we're just going to do it in terms of vectors. So we've got the resultant force, which is essentially the combination of these two forces. I've got a force that's going to try and drag this particle off in this direction, another force that's going to try and drag it in that direction. So how is this particle actually going to move? What's going to be our resultant? So we've got F1, which is minus 4i plus 7j. There's our horizontal and vertical components. And F2, 6i minus 4j. That's our again, horizontal and vertical components of that one. So, our resultant force is essentially, all we're going to do is just combine F1, F2, and put the two things together and see what's going to happen to this particle. So, if we add the two forces together to get our resultant, and what we're going to do now is just combine our I components, and then combine our J components. So what that tells us is when this particle moves, and because we've got a resultant force it's going to accelerate off in this direction over here, which kind of makes sense if you look at the diagram. Now, it says calculate the magnitude of R and the direction of R, direction between R and the vector I. R is a vector, but if we want the magnitude of the vector, we want the size of the vector, we need to know how big that vector is. So essentially what we're saying is, what is the length of that vector there? Okay, I've put this line in here because the second part of the question said we need the direction, what direction is going in, and we're going to describe that as an angle between R and the I direction, which is horizontal. So let's go for magnitude. How do we work out the size of a vector? Hopefully we should know that from our pure. Well, if I've got 2i going that way, 3j going that way, this is just a simple Pythagoras job. So the magnitude is going to be 2 squared plus 3 squared, which is root 13 newtons. And then the other part of it is going to be the direction. So we need to work out the angle theta, that angle there. So that's going to be a quick trig job. And we can use tan. So theta is tan to the minus 1 of 3 over 2. And so what we get is an angle of 56.3 degrees to the I direction. Right. Moving on again. So this one, again, a little bit more complex. So it might be you want to just kind of stop and just have a go at some basic stuff, some practice before we crack into something like this. But again, if you're feeling like you're okay with it, let's have a little look. So we've got the resultant force has a magnitude of root 68, and the resultant force is going to come from adding our two forces together. Okay. Now in this context we've got P's and Q's, so let's just proceed as if we knew they were numbers. So I've got 2pi here plus minus pi there, so my I components is just going to be P, and my J component is going to be that one there plus that one, so I've got Q plus 2, so that gives us the 2Q. Okay, so what I'm going to do now is just draw a diagram of my resultant vector and have a little look at what's going on using the information that we've got from the question. And so we've got that. So I've got my I component P, my J component 2Q plus 2, and there's the magnitude of the vector, which is root 68. So what I'm going to do now is take that information and turn them into some equations linking P and Q. So first off, we'll do a bit of Pythagoras. So we've got 68, i.e. root 68 squared equals P squared plus 2Q plus 2, all squared. So that's Pythagoras sorted. And then the other one we're going to do is, we know that tan theta equals 4, tan being opposite over adjacent. So we can say that 4 is the opposite over the adjacent. And what I'm going to do is just tidy that up a little bit, move the p over, and there we go, we've got 2 pieces of information. Again, it's a simultaneous equation job. So what I've got to do is figure out how I'm going to link these two things together. And what a lot of people might be tempted to do here with this equation is start multiplying out brackets and trying to tidy the things up and maybe get this thing as p equals. But we can take a big old shortcut here, because if you have a look at what we've got 4p equals 2q plus 2. And that 2q plus 2 is just sitting here. So all I'm going to do is, I don't need to do any more work. I'm just going to take this 4p, which is that, and just plug it into that one there. And that just keeps my life a whole lot more simple. So let's just do that. Those things are the same. Let's plug them in. So now what I've got is my equation just in terms of p. Do some squaring out, bearing in mind, of course, we're being very careful that when I do 4p squared, that's 4p times 4p, that's 16p squared. So that's why I've got 17p squared. Oh, where's my cursor gone? There it is. 17p squared there. And then do some rearranging and square rooting. We've got p equals plus or minus 2. Right. So that's that bit sorted. And we're told that since we've got an angle of theta that's between 0 and 90, that means p has got to be the positive version of 2. It's not going to be negative 2, because if p was negative 2, my vector would be going over here somewhere, and my angle would be greater than 90 degrees. So that tells us that p is positive 2, and so all I've got to do now is go back and figure out q. We'll get that from there, and that gives me q equals 3. So there you go. There's my answers.